Alright, now we're back into section 3. This is the video that picks up from where the last one left off, in that we were looking at graphs of some very basic logarithmic functions. And now we're going to consider what might happen if there's a transformation or multiple transformations done to the function. So I have this form here for a logarithmic function. Notice that I have a constant out in front. I have an h being subtracted from the x, and I have a k being added to that. This a here, of course, if this is negative, it's going to reflect it in the x-axis, and depending on if the absolute value of this is greater than 1 or between 0 and 1, is either going to stretch it or shrink it here. Greater than 1, it stretches it. Between 0 and 1, it'll shrink it. It'll kind of squish it down. On the other hand, this h, this is being subtracted from the x, so this is a horizontal translation. If h is positive, now that would look like x minus 5, because it has to have the minus sign there, so that would make h 5. Then you shift it to the right, h negative, so it would look like maybe x plus 3, because it's like x minus a negative 3. That would shift it to the left. On the outside here, if it's positive, then, and of course the plus sign here, so that would make it look positive. If it's positive, it's going to go shift upward k units, and negative is going to shift downward k units. So we have all those different things that can affect the properties of the function, and of course the graph of the function. So we're going to look at a graph first, and notice here it's circled in red, so this is one right off the review, although I think in the review it had the plus 2 in front, so it was 2 plus this. I just wrote it this way so it would maybe model more of what you might see in the textbook. Graph the function, identify the vertical asymptote, and write the domain in interval notation. Okay, now we're going to do some more stuff with domains here in just a second, but remember, when you take the logarithm of something, it has to be greater than 0. You can't take the log of 0, you can't take the log of a negative. So as far as the domain is concerned, that would mean that x minus 1 has to be greater than 0, or x has to be greater than 1. So the domain of g in interval notation would be from parenthesis 1 to infinity. Now, for just the logarithm base 2 of x, without the other transformations, because I have a translation here, horizontal, and I have a vertical translation, the vertical asymptote would be the y-axis. But this is a translation of 1 unit to the right, because it's in the form x minus the number, and the number is positive 1, x minus positive 1, and also 2 units upward from the plus 2. This is what I was talking about back here. Okay, now what I'm going to do is I'm going to make a quick sketch of what we did in the last video, and that is to sketch y equals, if I can write this all in, log base 2 of x. Now to do that, I changed this, if you remember, to x equals 2 to the y. Can you see that all? X equals 2 to the y. Yeah, it looks like it's showing up there. Alright, so x equals 2 to the y. I plugged in some numbers for y and solved for x. So I used negative 2, negative 1, 0, 1, and 2. Negative 2 gave me 1/4, 1/2, 1, 2, and 4. So now I'm going to sketch that. I know it's not what I'm looking for, but it's what I'm going to base it on. I'm going to sketch that in this color here. So if I graph 1/4, negative 2, it would be down here approximately. 1/2, negative 1 would be about here. 1, 0 would be here. 2, 1 would be here. And 4, 2 would be here. And I can draw the curve. Now, I'm not going to draw the curve. What I am going to do, though, because all I have are translations, is I'm going to use those 5 points to graph this curve, to find 5 points to sketch my curve. So I'll use maybe this color this time. And for each one of those 5 points, I'm going to go 1 to the right, and then I'm going to go up 2. So 1 to the right, up 2 would be right about here. That's this point. 1 to the right, up 2. This point would be 1 to the right, up 2 would be right about here. This point here would be, this brown point here would be 1 to the right, up 2, be up here at 2, 2. This, yeah, you can see that, okay? And then let's see, this point here, which is at 2, 1, would be 1 to the right, up 2, so that would be at 3, is that 3, 3?
up to 3, 3. Let's see if I can draw this. Here we go. And then my last point here, which is at 4, 1, or excuse me, 4, 2, supposed to be a 2 there, would be to the right one at 5, and then up 2 up here at 4. And without getting around and looking at it, there's my guy. Now remember, the vertical asymptote for the one in brown was the y-axis. So in this case, it's shifted over 1. My vertical asymptote would be the line x equals 1. And my graph, and I'll do this through those red points in black here, would look like this. Now that's a little awkward there, and hopefully you can see that okay. And it's going to get closer and closer and closer again to the y-axis, or to the, not the y-axis, but the vertical asymptote of x equals 1. Let's see, did we answer it? We graphed it, we identified the vertical asymptote, and we've written the domain in interval notation. So this one's covered. This is just like what you might expect to see on your semester exam. Over here, the domain of a logarithmic function is the set of all real numbers that make the argument positive. That's what I was talking about back here when I found the domain. The argument, of course, is like what you're inputting. So this would be the argument. This would be the argument. This would be the argument. Okay? Now, we're to write the domain in interval notation. And just like I did with the last problem, I'm going to set the argument greater than 0. I'm going to set the argument greater than 0. I'm going to set the argument here greater than 0. Well, this one solves nicely, and so does this one. I would subtract 1 from both sides and divide by -3. That's going to reverse the order. And I'm going to write my answer in interval notation, so it's from -infinity to 1/3. And don't forget the parenthesis, because we're not including the 1/3. That would make it 0. Over here, it's even simpler. And this, again, these two come right off the review. If I add 5, x is greater than 5 would look like 5 comma infinity in interval notation. And so we can call that the domain of f. The domain of f. And then over here, we've got a little bit of work to do because this is a quadratic inequality. As it turns out, it factors nicely, which is always good. Set each factor equal to 0 to find your key values. We talked about this before when we're solving polynomial inequalities. So I said x minus 5 equal to 0, x plus 2 equal to 0. I get x is 5, I get x is -2. And then I'm going to draw a number line. I'm going to put -2 and 5. I'm going to pick a test point, and I'm going to check to see if it makes this expression, or this expression even, positive or negative. If I take a number like 10 and plug 10 in, that would be a positive times a positive. If I take a number from here like 0, that would be a negative times a positive. And if I take a number over here like -10, that would make that negative, and that would make that negative, which is positive. Well, again, it's got to be greater than 0. So that would be this part here and this part here. So the domain of this function is from -infinity to -2, and then from 5 to infinity. Non-inclusive. Don't include the -2 or the 5. You can't take the log of a negative number. If I said, okay, what's the log base 10 of -5? Well, it would have to equal a number x such that if I convert this, -5 equals 10 to the x. Well, there's no way you can take a positive base, raise it to a power, and get a negative number, or 0. So that's why it has to be greater than or equal to 0, or excuse me, greater than 0. It has to be positive. All right, the last example there's a lot of writing there, didn't leave much room for the actual work here. But what I'll do is I'll do some of the work over here. I'll erase a little bit of this to get it ready. All right. And we'll start. Logarithms are useful when dealing with very large, very small, and positive numbers, of course. An application of that involves the idea of the Richter scale on a seismograph. The intensity I, capital I, of an earthquake is measured in the seismograph by a device that measures the amplitude of the shock waves. I sub 0 is a minimum reference intensity of level earthquake against which the intensities of all other earthquakes may be compared.
The magnitude of an earthquake of intensity I is given by this. Notice the logarithm, and it's a common log. M equals, let me write that down over here, because I'm going to need it, the log of I all over the reference point. Remember to mention the minimum reference intensity. Okay, A, determine the magnitude of an earthquake that is 10 to the 5.2 times I sub 0. Well, that means I, in part A here, I is equal to 10 to the 5.2 times I sub 0, times its reference. So what I'm going to do is I'm going to plug that in here, and I get the log of 10 to the 5.2 I sub 0 over I sub 0, which is, the I sub 0's cancel, the common log of 10 to the 5.2, and using the basic properties of logarithms, since it's base 10 and this is a base 10 exponential expression, this is going to give me 5.2. So, determine the magnitude, well, it'd be 5.2 on what we call the Richter scale. Okay? Part B is very, very similar. There's one little change there, and that is instead of 5.2, it's 4.2. So if I went back through this and changed just this for part B here to 10 to the 4.2 times I sub 0 all over I sub 0, they would cancel. I'd get the log of 10 to the 4.2, which is 4.2. I'll put that over here. So we hear on the news all the time about earthquakes and about their magnitude. Well, this is how we're determining this. Now it says here in part C, this is a little bit different, so this might be a little bit more interesting for you. How many times more intense is a 5.2 magnitude earthquake than a 4.2 magnitude earthquake? Well, all you want to do here in part C, if I can squeeze this in, is to compare them, how many more times. So I'm going to take 10 to the 5.2 I sub 0, and I'm going to divide it by 10 to the 4.2 I sub 0. So this is 10 to the 5.2 divided by 10 to the 4.2. Property of exponents, this is 10 to the 5.2 minus 4.21, or 10. So this is 10 times more powerful. Here, I'll put it down here. Now this is just one example of a use of logarithms. There's others in physics. You'll be dealing with them just as much. But be sure to look over all the different kinds of application problems. Practice, practice, practice.